The word recursive really just means self-referencing. And in computer programming, when people use the word recursive or recursion, they're usually talking about a recursive function, which is the name we use for a function that calls itself. And while that explanation is simple enough, it doesn't quite honestly capture the complexity hiding underneath. You probably wouldn't be surprised to learn that NASA, the American government agency focused on spaceflight and aeronautics, has internal safety critical code standards, 10 rules that they refer to as the power of 10. But you might be surprised to learn that don't use recursive functions is literally rule number 1. And the justification they give for this prohibition is that recursive control flow makes code harder to analyze. In other words, it makes it harder for software tooling to understand what's going on. But it's not just software analysis tools that find recursive functions hard to understand. If you've ever done a university computer science degree, you'll know that recursion is one of the first points where students really start to feel out of their depth. A certain percentage of people just find it very difficult to understand. And I think that whenever there's a sudden and predictable cliff like this, where a number of students all start to struggle at the same time, it's a clue about a flaw in the underlying design of the material. In this case, I think the clue is pointing to the fact that recursive functions actually work by exploiting a number of lower-level features in structured programming languages. And if you don't understand how that lower-level machinery works, it can be very difficult to wrap your head around what's actually going on. So we'll start very small and we'll peel back the layers of the onion one by one. The most basic implementation of a recursive function is a function that takes no arguments, returns nothing, and only does one thing, which is call itself. And even if you don't feel confident with recursion, you can probably predict that if we run this, it will just crash the program. But wait a minute, why does it actually crash? If we think about this code in purely abstract terms, surely it should get stuck in an infinite loop that never returns, rather than crashing, right? Well, the crash message itself can start to give us some insight into what's going on. And the reason for the crash is the now infamous Stack Overflow error, which of course is what the famous question and answer website Stack Overflow is named after. Now, it might not seem like it, but this is actually a very well-named error. The problem is that at the point in the curriculum that recursion is first introduced, often students have no idea what either a stack or an overflow actually is. An overflow in programming is exactly analogous to an overflow in real life, which happens when something inside a container becomes too large and spills out over the boundaries. And in programming, when this happens, we usually put the name of the container first and then the word overflow after. An integer overflow happens when we run out of digits to represent a number that's too large. A buffer overflow or an array overflow happens when we run out of slots in our array to fit all our elements, and as a result, you can infer that a stack overflow must mean we've run out of space inside whatever a stack is. So we know a stack must be a container of some kind. But when I look at my recursive function that's apparently causing the stack overflow, I can't see any data that would need to be stored anywhere. The program has no variables at all, so where is the data? What is it that's actually filling up and overflowing? Well, it's actually hiding inside this function call statement. If you imagine a simple program executing one line at a time from top to bottom, when you call a function, the control flow needs to jump from the call site into the body of the function you've called. It doesn't quite work like this under the hood, but if you imagine it in terms of line numbers, the compiler replaces this function call with an instruction that says jump to line 78, which is the start of the function. But what about when the function is finished? When a function returns, the program needs to jump back from the end of the function body to just after where the function was originally called from. Now, this would be slightly more tricky, but still very possible for the compiler to figure out if the function was only ever called in one place. You just jump back to the only call site. But if a function is called from two possible places, how do we know which of those two call sites to go back to when our function returns? We can't just replace that return statement with a jump to line number because there's two possible line numbers to return to. Well, the compiler is actually doing something sneaky under the hood. Whenever you call a function, the compiler is inserting an invisible operation that stores the address of the call site in runtime memory, which is referred to as the return address. Then when your function reaches the return statement, underneath your program is reading that stored return address so that it knows where to jump back to. But that idea is a little bit oversimplified. If we only have a single return address, what happens if before we reach the return statement in our calculate discount function, we call another subfunction? The nested subfunction call would overwrite the return address so that by the time we arrive at calculate discount's return statement, we've lost our original address and can't figure out how to make it back to our getFinalPrice function. And so it's obvious that we need to store multiple return addresses at the same time, which means we now need a data structure to put those return addresses into. We can see the requirements of this data structure very clearly. We need to be able to add a return address to this data structure when we call a function, and we need to be able to remove that address again when we return from that function. As you can imagine, this data structure needs to have excellent performance and memory usage characteristics because we interact with it on every single function call and return statement. And I know that feels like a tall order, but luckily there's a natural characteristic of the way that functions work that we can exploit here. Imagine I have my main function, and inside that I call a child function. If you can read code, you intuitively understand that the child function has to return before the parent function returns. And it doesn't matter how many levels deep we go. If I call a grandchild function inside my child function, we know the grandchild function has to return first, and then the child function, and then the main function. This is one of the fundamental properties of synchronous programming, which is that nested functions return in the opposite order that they're called in. The call order here is main, child, grandchild, and the return order is grandchild, child, main. Remember how we talked about the requirements of our return address data structure previously? We saw that we needed to add a new return address every time we called a function and remove that address again when the function returns. If we merge our requirements with our observation around functions, we can see that the return addresses will be added in a particular order as functions are called, and then removed in exactly the reverse order as those functions return. An even simpler way to describe this behavior is that if we're putting our return addresses into an array, addresses are only ever added and removed from the very last position. And an array where you only ever add and remove elements at the very end is called a stack. Now, stacks are of course a generic data structure that you can use for your own programs, but when people refer to the stack in programming, what they're talking about is a hidden stack data structure that's managed by the programming language that adds new data when functions are called and removes it again when they return. And so now that we understand both halves of the definition of a stack overflow, it's easy to see why this code crashes instead of running forever. Even though there's no arguments, variables, or return values, there's still hidden data being created. Our recurse function calls itself once, which pushes this return address onto the stack. But before the child function returns, it calls itself again, which pushes another return address onto the stack. This continues infinitely without any of the subfunctions ever being able to return, which means we never remove any of those return addresses from the stack. Eventually, we completely use up the finite amount of memory that was allocated for the stack in the first place and cause an overflow, hence the name of the error message. So now that we understand why, how, and where the return address is actually stored, it's trivial for us to expand our recursive function to actually do something. We're going to write a function that can search through a nested folder structure, matching file names to a pattern and printing the matching files to the console. We'll start with the arguments for our function. I'd say at the user level, they might want to call findFilesMatchingPattern with the file path that they want to start searching at, as well as a string pattern or regex to match the file names with. So the user wants to search inside their documents folder and they want to find all the files with the word cat in the name. So they call our function providing two function arguments. These function arguments are exactly like the return address in that they need to be stored somewhere without overwriting the arguments of the current function. So in addition to pushing the return address onto the stack, we can also push the value of the two function arguments onto the stack as well. And this mixed data of arguments, return address, and potentially other things too is referred to as a stack frame. And even though we use different names for them, the stack is essentially just an array of structs or objects that contain data about each function call. So jumping into the body of our new function, how should we approach this? Well, the first thing is that a file path the user provides could point either to a folder or just to a single file. So we'll look up the provided path, and if it's a regular file, we'll match the file name to the pattern the user provided and return. If the path points to a folder, what we want to do is list all the folder items, that is, any files and/or nested subfolders. This gives us back an array of data that we can iterate through with the loop. And here's where a recursive function can make things feel a bit magic. For each of these nested folder items, we're just going to call our findFiles function recursively, and because our function takes arguments, we can instead call it with the path of the nested folder item and the same pattern match. So what happens underneath is that we push a new stack frame with the return address and arguments onto the stack and jump into a new instance of the same function, but this time with a different path. In this case, a regular file called notes.txt, which is the first file inside the documents folder. And because notes.txt is a regular file, that means that this first if statement is going to return true, so we're going to do the pattern match and return. This returns us to the previous call of our findFiles function, removes the top stack frame from the stack, and we continue to our next loop iteration. But hold on a second. If all we have to go off is a return address, that's basically the equivalent of just jumping to a random point in our program. And if we were to just jump straight to this point in the function using a goTo statement, we would have skipped over all this code above, which means our file, folder items, and even our loop iteration variable I would not have been initialized. That means that the state of these local variables also needs to be saved somewhere when we jump into our subfunction and restored again when the function returns. It's clear from what we've learned so far that just like the return address and the function arguments, we can store the values of all of our function's local variables inside the stack frame as well. As a result, when local variables get modified, like incrementing our loop variable I, we're modifying our data inside the stack frame. Then later on, when our subfunction returns and we remove the top frame from the stack, all our previously modified local variables are still there. So we can continue on right where our loop left off. So our loop continues on to the next item in the Documents folder. Photos is a folder, so we enter this second branch, and the same process repeats again, with the items inside the Photos folder. We jump into a third level of recursion, matching each of the file's names one by one against the pattern, printing the names of those that match, and then returning. When we've iterated through the items in the Photos folder, the function returns back to the Documents folder, and we resume processing its items. You can see how this pattern continues on and will recursively traverse into all the subfolders, eventually returning after printing all of the matching files. It's amazingly powerful for how concise the actual code is, and there are so many fascinating things to unpack here. The first observation is that in contrast to our original example that caused a crash, a Stack Overflow error, this recursive function we've written to match files doesn't crash for some reason. I'm sure you can intuitively feel the difference between that example and our file search, but let's dig into the why. Our first example generated a Stack Overflow error because the addition of stack frames was obviously unbounded or infinite. It's not possible for this function to return before it calls itself. By contrast, if we look closely at our findFiles example, there are two separate code paths in which our function can avoid calling itself. If the path points to a regular file, the function returns early without calling itself recursively, and this one is less obvious, but if there are no items in the directory at all, that is, if the directory is empty, the function will return naturally without ever entering the loop. I'm going to amend my initial definition of a recursive function just slightly. Rather than being a function that calls itself, a recursive function is more accurately a function that might call itself. Inside our recursive functions, a code path like these two we identified, in which the function avoids calling itself and instead returns, is referred to as a base case. And a base case is a condition under which the recursive function calls will stop going deeper and instead start to return back upwards. This means that these cases reduce the size of the stack rather than increasing it, which is obviously an essential part of avoiding a stack overflow. The second interesting observation is actually about the structure of our files and folders. Remember how I mentioned that recursive just means self-referencing? Well, if I asked you to define what a folder is, you would probably say something along the lines of, a folder is a container that can have multiple items inside it, which can either be files or more folders. Notice how the definition of a folder refers to the concept of a folder in its definition. It's self-referencing. And as a result, the term we would use to describe a folder like this is a recursive structure. And that's really interesting because we can have recursive functions which call themselves, as well as recursive structures or recursive types which reference themselves in their definition. Now you might be wondering, is there a relationship between these two concepts, recursive functions and recursive structures? There sure is, and it'll reveal itself once we explore in a little more detail. So we learned that a folder is a recursive structure. And in more abstract terms, this type of recursive structure is called a tree because of the shape it makes when visualized like this. Conceptually, a tree is built out of a self-referencing object called a node that has a single reference to its parent and multiple references to children, just like our folder structure does. So if we want to perform a task like matching file names against a pattern, what we're saying in tree terms is that we have to visit each node in the tree exactly once to check if it's a file and compare its name. And the particular order in which we choose to visit each of these nodes of our tree is called a traversal. So given that our recursive function is obviously visiting all the nodes in our folder tree because we're seeing the correct matching output printed, what kind of traversal is happening here? I'm just going to change our recursive function slightly to always print the current path so it's easier to see what's going on. And if I put in some indentation, you can see that the recursive function is visiting the nodes in the folder tree in exactly the same order as the visual representation on the left-hand side. This type of tree traversal is called a depth-first traversal. And the reason it's called that is because in tree terms, we always visit all the children of a node before visiting its siblings, which means visiting the entire subtree underneath the Photos folder before we even look at the Downloads folder. We go as deep as we can down a branch before trying out other branches, hence depth first. And the reason this is so interesting is because there's nothing visually obvious in our code that indicates we're going to do a depth-first traversal. It turns out this is actually an emergent property of all function calls that's incredibly important to understand. Starting from the main entry point, the function calls in every program naturally form a tree. And because of the way that child functions need to return before their parent can continue, the execution of your program itself is a depth-first traversal through the tree of function calls. And as a result, all recursive functions are actually just an elegant way of doing a depth-first traversal over a tree structure, which is why they work so well for doing something like searching a tree of folders. Now that we're familiar with why this type of data structure is so easy to traverse using a recursive function, let's extend the functionality a little bit. Say we wanted our find function also to count how many files match the search pattern in total. There are a few ways to do this. The first way is often the instinctive approach that people use when approaching recursion and relies on global variables. We simply declare a matched files count variable in an outer scope visible to our recursive function, and then every time we see a match, we increment the global count by 1. The second approach is a little bit more tricky and is sometimes what people refer to as pure recursion. Instead of having a global variable, our function now returns an integer, which is the total count of all the matched files and folders. In my experience, adding a return value to a recursive function is where people start to find them really confusing. And it's easy to see why when we look a little closer. By definition, our top-level function is supposed to return the count of all matched files and folders. But how do we actually do that? Well, if we think about our folder tree, we can see that we can't know how many files are in our Documents folder until we know how many files are in the Photos folder. And we can't know how many files are in the Photos folder until we know how many files are in the Cats folder, and so on. In abstract tree traversal terms, This means we can only calculate the value for a node once we've calculated the values for all of its children, which in turn means that the only place that we can start is nodes that have no children at all, either files or empty folders. In tree terminology, these are referred to as leaf nodes. This traversal order, which starts from the leaf nodes in the tree and only goes back upwards once all the children have been visited, is called a post-order traversal. You can basically imagine it as doing a depth-first traversal and then retracing your steps. And as we saw, because function calls are naturally a depth-first traversal, there's a very elegant way to express this type of post-order traversal as well. We know that in our top-level function call in our documents folder, after this loop finishes, we've descended into all the possible subfolders. So any code that we run after all our recursive calls will naturally run in post order. To put it visually, any code before the recursive call runs on the way down a tree, and any code after the recursive call runs on the way back up. So to sum up the total number of matched files at the top of the tree, we start by defining a local variable to count our matched files. If we're looking at a single file and its name matches, we can just set the count to 1. If we're looking at a folder, we add each of the returned file counts of the folder items as we're iterating through the loop. And finally, at the end of the function, we've traversed all the subtrees to the bottom and up again, which means we can return the matched file count, which for the top-level function call will correctly reflect the count of all the matched files in the tree. This is a very succinct and compact way to return aggregated information from a recursive function, but I find it to be a bit clever, and in my experience, this type of return value aggregation is the point at which recursive functions start to become very confusing for newer programmers. And it's no surprise, really. The split nature of recursive functions means that you have the first part of the parent code run, and then all of the recursively nested child code, and then the second half of the parent code. It's very easy to accidentally confuse the order of execution and introduce a subtle bug. So to make this a little easier to understand, I like to use a third approach, which is a compromise between using a global variable and using this post-order traversal aggregation. What we're going to do is define a struct or an object that contains our matched files count. And we're going to change the signature of our recursive function to also take our result data as a parameter. In C-like languages, we would pass our result data by a pointer, and in other languages, you would use a reference type like an object in JavaScript, for example. And that's important because we don't want a new copy of the result data every function call. We can then increment our matched files count when we find a match and simply pass the same reference down to nested recursive calls. This way, we don't have to worry about mentally visualizing the post-order traversal and aggregation, while still avoiding the pitfalls that come with using a global variable. Passing a container of data down through a function call stack like this is often referred to as a context. And some programming languages have a context feature built in, so you don't need to manually pass it down. In real-world situations, I've found this type of context to be incredibly useful for recursive functions, and not just for return values. Now, the more experienced observers may have noticed that we have a bit of a ticking time bomb waiting for us in this function that traverses folders. While it's simple and convenient to imagine a file system as only having two objects, that is, files and folders, reality is not that simple. Our folder here is a perfect example of something we might refer to as a leaky abstraction. As well as files and folders, file systems typically support an additional item type, which is called a link. A link works just like a link on the internet. Rather than directly storing a file or a folder, a link points to a file or folder stored somewhere else. When we're iterating through our folder of cat photos, what happens if we encounter a link that points back to our top-level documents folder? Our recursive function will happily loop back around infinitely until we run out of stack space and get a Stack Overflow error. Now, it's technically possible for us to detect and ignore links, but that's not actually the correct behavior either. Imagine if inside our Photos folder, we instead had a link that pointed to some photos on an external drive. We would expect that searching within our Photos folder would also search the drive, so we do need to follow those links. What we need to do here is detect if there is what we would call a cycle or a circular reference. And the easiest way to detect a cycle is just to push the file path of every file we see into a hash map or a hash set, so that if we've already seen the file before, we can return and short-circuit our infinite recursion. Because we've already got our context struct, we can put a reference to our file name cache in there, and it's available for us to use throughout our recursive functions. But just because we can design our recursive function to prevent infinite loops, doesn't guarantee that we're never going to get a stack overflow. And that's because the stack still has a finite size. And on most platforms and environments, it's actually much smaller than you would think. The default size on a 64-bit Windows machine is only 1 megabyte. I went and did some napkin math on one of my projects that traverses a folder structure in C, and the function that processes each folder item has a stack frame that's 2 kilobytes. Which means that you only get around 500 nested recursive calls, in other words, a function call tree that's 500 levels deep, before you completely exhaust your stack memory and you get a stack overflow despite not having an infinite loop. Now, 500 levels of folder nesting might seem like an absurd amount, but there are plenty of examples of recursive structures like graphs and search trees and linked lists that can easily reach that level of recursive depth. I've personally worked on a piece of production software that did recursive processing of documents uploaded by the user, and there were several occasions where a user uploaded a legitimate document that we couldn't process because the server would crash with a Stack Overflow exception before it got to the end. Now, there are technically ways to mitigate this problem. It's sort of possible on various operating systems to detect at runtime how large the stack is and how full it currently is. But even if we could accurately predict that a stack overflow is about to happen, if we're still processing legitimate data, our only option at that point is to return early, which will result in some of the data just not getting processed and potentially incorrect results. And so it's starting to become clear why, when developing a safety-critical code standard like the one at NASA, it makes sense to prohibit something like recursive functions. Despite the fact that they can produce very visually elegant implementations when we're traversing a recursive structure like a tree, recursive functions have some major downsides, mainly the counterintuitive order of execution, the fact that it's very easy to accidentally make a mistake with your base case or in your cycle detection code and get into an infinite loop, and having to deal with the limitations of the stack memory, which differ depending on your platform and configuration. These days, personally, I hardly ever use recursive functions, and that's because once you understand how they work under the hood, it's remarkably straightforward to convert them into a form that doesn't use recursive function calls at all. And in technical terms, we would often refer to that as converting a recursive approach to an iterative approach. And for a nice practical example, we're going to convert the recursive function we wrote to search through folders into one that uses iteration instead. Just to refresh, whenever you call a function, all the data related to that function call, the arguments, local variables, the return address, it's all put into a stack frame and pushed onto the top of the stack. And when the function returns, the stack frame is popped off and the new top stack frame is resumed. Now, this stack is managed automatically by the programming language, but there's absolutely no reason why you can't just create and manage that stack yourself with your own code. So the first step to converting a recursive function into an iterative one is to create a stack data structure. Now, we saw that the way that a standard program runs is it keeps processing the function on the top of the call stack until eventually the main function returns and we exit. So the way that we can represent that is by creating a while loop with a condition that the stack isn't empty. That is, it has at least one stack frame left in it. And each iteration of the loop, we want to be processing the top item in the stack, which would represent the currently executing function. If you're not too familiar with stack data structures, the terminology for the combined operation of reading and removing the item on the top of the stack is pop. If you look closely, our function currently does nothing, as this not empty condition here will always fail. So to get started, we need to push our very first stack frame onto the stack, which is the equivalent of the very first top-level recursive call. Remember how we were searching our documents folder for files that matched cat? We know that function arguments get stored in the stack frame, so we'll push those arguments onto the stack to get started. We've now got enough in place to do some actual work, so we'll put the first bit of code in to resolve the path and print the file name if the file matches. If we compare our current iterative approach to our initial recursive one, you can see the code is very similar. The main difference is that we're explicitly accessing the function arguments in the stack frame that we're managing, rather than the programming language managing that memory for us. Now you might be able to see it, but we already have an example of a nice little optimization we can do with an iterative approach. We're actually matching every file against the same pattern because that's how search works. And that means that in our recursive implementation, we pass the pattern argument directly down into the next call without modifying it, resulting in a redundant copy and extra memory usage for each recursive function call. In our iterative approach, we can easily lift that variable out of the stack frame and just have it in scope outside the loop. There's a nice general rule here, which is that if a recursive function argument is transparently passed down into child calls, it doesn't need to be stored in the stack frame when we're doing an iterative approach. It can be lifted into the outer scope. So this is looking good, but obviously this while loop will only run once, as we're immediately popping the root stack frame without pushing any new ones. What we need to replicate next is this section, where we actually do the recursive call on the folder items. So what's the equivalent of that in our iterative approach? Well, what is calling a function? It's just pushing a stack frame and then jumping to that function code, right? So the equivalent in our iterative approach is to loop through the folder items and just push a new stack frame onto the top of our stack containing the path of the folder item. So in our first iteration, we push the 3 items inside the documents folder to the top of the stack, and then we continue on with our while loop. This time, because the downloads folder is on the top of the stack, we'll be processing that next. But hang on a minute, wouldn't we expect the notes.txt file to be processed next, as it's the first item inside the documents folder? Yes, and this is a quirk of the way this kind of stack-based iterative approach works. Because if we iterate the children in order and push them to the stack one by one, the last child will end up being on the top, which means it will be processed first on the next iteration. So if we want to process these subfolders in the same order as the recursive approach, we just push them in reverse order onto the stack instead by reversing the order of our iteration, so the first item ends up on the top. So we continue on to the next iteration of the loop, which pops this notes.txt file, which of course has no children. We do the match, we skip adding any new stack frames, and just keep iterating. When we get to the photos folder, we can push its contents onto the stack, and you can see how on our next iteration, we'll process these 3 photos in order, exactly how we would have in our recursive approach. And that's actually it for our conversion. If we compare our complete iterative and our recursive approaches side by side, it turns out that for this case, we only need marginally more code for our iterative approach, and we avoid all of the problems that come with using recursive functions. Now, we could finish up here, but I want to dig a little bit further. This might sound like a weird thing to say, but don't you feel like the conversion from recursive to iterative was a little bit too easy? Remember this graphic from earlier on? It turns out there are some tricky things that you can do with recursive functions that make converting them to an iterative form a little bit more difficult. We've implemented a replacement for our function call stack, and we've got our depth-first traversal working. But what about post-order traversal? Remember how we saw that everything that happens before the recursive function call happens in depth-first order, going down the tree, and everything that happens after the recursive call happens in post-order, that is, going back up? That might seem a bit abstract, so I'll give you a direct example from our directory traversal. Imagine that we're using some kind of API that requires you to open a folder to interact with the contents and then close it again after you've finished with all the files inside, including nested folders. So to adhere to this API in our recursive example, we would open the file, do all the recursive processing of nested folders, and then close the file afterwards. In terms of our tree traversal, opening the file happens on the way down in depth-first order, and closing the file happens on the way back up in post-order. Our iterative approach currently doesn't support this because we only ever process each stack frame once. For example, we push the initial documents folder onto the call stack, but then immediately pop it off before pushing the folder items, so there's no way to revisit it after we've recursively processed all of its children. Instead, what we want to do is change this pop to a peek call, which is just stack jargon for getting the element on the top of the stack without removing it. As a result, now when we push our folder items onto the stack, they're on top of our documents folder, which means that we'll revisit the documents folder after we've processed all of its items. There's one problem though that you might already be able to see. On our next iteration, we inspect our notes.txt file on the top of the stack. But because we're just peeking it rather than popping it off, when we head around to our next iteration, it's still on the top, and as a result, we're stuck in an infinite loop. Oops. The fix here is quite straightforward. In our branch for matching files, we simply pop the top frame off the stack when we're done, and we've solved our problem. We can now continue on to the Photos folder, which pushes its 3 items onto the stack, and because all 3 of them are files, they are all inspected and then popped off, and eventually we get back down to the Photos folder again, inspecting it for the second time. But now we have another problem. If we just continue with our existing implementation, we'll push the Photos folder items back onto the stack, and we're stuck in a slightly more drawn-out infinite loop again. Unlike files where we know they're always popped off the stack immediately, folders need to be visited twice. Once in depth first order on the way down, and once in post order on the way back up. We only want to pop them off the stack on the way back up. So what we're going to do is add a visited boolean to the stack frames that will default to false. If the folder hasn't been visited before, we'll push the items and set it to visited, and if it has been visited before, we'll pop the folder off the stack. This allows us to progress correctly to the end of the algorithm. This branch that we take if the folder's been visited before is equivalent to the post-order traversal code that happens after the recursive function call. And so finally, to implement our original requirement of closing the file after we've finished with all its children, we can put our close file call into the post-order branch and we're done. We now know how to emulate depth first and post-order traversal using iteration, but what about return value aggregation? Remember I showed you that tricky way of summing up the total count of matched files by returning the aggregated count in our recursive function? We of course could circumvent this particular case by passing a context struct like I showed you earlier, but sometimes there are cases where we want to use these aggregated return values at each level of the tree rather than just getting the final answer back at the very end. As an example, say I wanted to display a badge on each folder that shows the total count of matched files in all the subfolders. The Photos folder shows 2, the Downloads folder shows 1, and the Documents folder shows the aggregate, which is 3. In our recursive approach, we could update the file count using the child matches variable because at this point it contains the total summed child matches from all the recursive calls below it. But how do we implement something like this in our iterative approach? So in the same way that we emulated the function callStack and function arguments, now we want to emulate return values. And if we want to emulate something, the first step is to understand how it actually works underneath. Return values by definition are accessible from both the parent function and from the child function, which means they need to be stored in some shared space that can be accessed by both functions. Now, in some cases, the child function will write the return value into a specific hardware register that the parent function will read from, and in some cases, the parent function will pass a pointer in the child function's stack frame to where the return address should be written to. There are a number of possible implementations. But the important thing to take away from this is there needs to be some shared place that the child function can write to and the parent function can read from. So if we return to our implementation, just like for real return values, there are a number of ways in which we could introduce a reference from parent to child. We could do something as straightforward as simply attaching a reference to the parent stack frame to every child stack frame. This is essentially converting our stack frames into a recursive structure themselves, an explicit tree structure. That way, when we find a matching file, we can simply use the parent reference to increment the parent's matched file count by 1. And as a result, when we visit our folders for the second time in post order, we'll have the correct count to use for setting our badge, before we add the entire folder's count to its parent too. There are, of course, many different approaches you can use here. You can push return values into a separate stack and pop them off in post order. You can keep a reference the other direction from parent down to child. But in a general sense, the important thing to remember is that if you want to use your return values part of the way up the tree, rather than aggregating them all up to the top, there needs to be some kind of shared storage that both the parent and the child stack frames can access. With these tools up your sleeve, you'll be able to convert a very significant proportion of all the recursive functions you see out in the wild into iterative versions. But we're not quite finished. Rather than trying to give you a direct explanation for this last one, I'll let a particular example speak for itself. File systems, of course, aren't the only type of data that we deal with that naturally fits a tree structure. Another very common case is user interfaces. If you imagine a scrollable feed of posts like this, it might not immediately look like a tree structure. But underneath, in terms of the data that we're dealing with as programmers, this interface is likely represented with a tree structure something like this. with smaller inner elements nested inside larger outer ones as children. Notice how none of the elements are crossing over the boundaries of each other? Inner elements are completely contained within outer elements. And this is a very important property for building flexible user interfaces that can stretch or shrink to the size of their content. Rather than having to explicitly set the dimensions of this outer grey container, we can instead say that it should fit to the size of its contents. And to think about that another way, we can say that the size of our outer container is defined as the sum sizes of its children, which in turn are the sums of their children, and so on. And of course, what we're describing here is a recursive operation. Let's put some basic code together to calculate the sizes of our elements. Starting with the outer grey rectangle at the root of the tree, we call our updateElementSize function, which we expect to recursively calculate the size of every element in our tree. It's worth mentioning that I have a couple of other videos with a comprehensive look into how UI layout works, so I'll be working in very rough details here. Our simple function first figures out some base minimum size for our element, taking padding and that kind of thing into account. And then it loops over each of the children, calling updateElementSize recursively. You can see that we're expecting the function to return the size of the child element so that we can sum the results together to calculate the size of the outer element. We can now recognize this as return value aggregation. It then returns its total size, which includes all the elements below it in the tree, back to the parent, which allows the recursion to work correctly. Now, this is all very straightforward, as it's almost exactly the same strategy we use to sum up the total number of matched files in our folder search implementation. But here's where it starts to get a bit tricky. If we want to draw our interface correctly, we need to know not just how big our elements are going to be, their dimensions, but also where they need to be drawn on the screen, their position. But watch what happens when we increase the font size of our recent post's title text. Notice how everything below the title needed to move downwards to make space for the larger text? What we've realized here is that position has a dependency on size. And more specifically, if we look at the tree view again, we can see that the size of our title element affects the position of all of its subsequent siblings. The posts that appear afterwards all need to be moved down. To make matters worse, because we know that the size of an element depends on the size of its children, it means that the size of a child affects the position of its parent's siblings. See how the second post needs to move down in response to an image inside the first post getting taller? In simple terms, what this boils down to algorithmically is that we can't determine the position of an element until we've already visited the entire subtree under all its previous siblings. And now to actually implement this in our recursive function is very simple. Because we want our function to size and position our elements, we're going to change our function to take the current XY offset as an argument. We'll use that offset to set the on-screen position of the current element, and of course we'll have to change our recursive call to also include the offset. Now here's the really neat part. We add the child dimensions returned by the recursive call to our offset, and the new offset will be passed into the next child on the next iteration of the loop, which is how the size of one sibling affects the position of subsequent siblings. To visualize how this looks, our offset starts at 0, and then after we finish with each child element, we add its dimensions to the offset, which allows us to place the next child at the correct position. Now, a real layout algorithm is a little more complex than this, but this gives you the general idea. And the reason I bothered to explain all this to you is because although it may look simple, this recursive implementation is actually exploiting another quirk of the way functions are called that currently isn't supported by our iterative approach. We can divide this recursive function up using our previous strategy. Everything before the recursive call happens in depth first order, and everything after happens in post order. But here's the thing, say our parent element had 3 children. If we unroll this loop and implement all 3 iterations by hand, essentially just copy-pasting the loop body 3 times, look what happens. We end up with multiple recursive calls with code sandwiched in between them. With only one recursive call, it's clear the order in which things execute, but what about with multiple calls? You might remember back at the very beginning of this video, I demonstrated how function calls in every program naturally form a tree, and showed the order that the functions were called in. Well, it turns out that doesn't quite tell the whole story. Because watch what happens if we keep track of the actual line of code being executed and where it is. Things progress as expected and we call down into the truck function, and because that function's empty, we return to the apple function, visiting it again in order to continue execution. Before it eventually returns, the apple function is visited 3 times. Of course, the same thing happens as we return to our lemon function. It's visited a second time before progressing on to the pear function. And that means if we place some extra code into the lemon function between the call to apple and the call to pear, that extra code will execute after this entire first subtree is executed, but before this second function starts executing. Now, this visualization probably looks familiar to you because it's exactly the same as the logic we needed to use to compute the position of our UI elements. And so returning to our recursive function with our unrolled loop, we can see that the code after each of the recursive calls runs after we've completed processing one of our entire subtrees, which is what allows us to correctly calculate the offset position and then pass it into the next recursive call as an argument. So it's really important to be aware of how recursive calls inside loops work. The entire subtree for each child will execute before the next iteration of the loop or any code after the recursive call. And so now that we understand how this recursive function actually works, it's time to develop our iterative equivalent. I've converted it using exactly the same strategy that we used earlier. As expected, we're putting a reference to the parent into the stack frame so that we can do return value aggregation on the sizes. And we're also putting the offset into the stack frame because it's one of the function arguments in our recursive approach. But this approach won't work because of a subtle difference between how our recursive and iterative approaches are implemented. When we look at a function call hierarchy like this and how many frames are pushed onto the stack, we start with our top-level lemon function. When it calls the apple function, we push that stack frame and jump. Apple then calls the truck function, we push that and jump again. Truck doesn't call any subfunctions, and so it returns, popping off the stack frame. We revisit apple, which then calls the car function, which gets placed onto the top of the stack again. By contrast, let's look what happens when we have an equivalent iterative approach. We start by pushing the initial top-level stack frame, but then, as you can see, we push all the child stack frames in a loop. This is basically the equivalent of pushing all the stack frames on this second level of the tree at the same time. Now, because we only process the very top frame on the stack, the order in which we first visit these functions is still a depth-first traversal. However, there's one key difference. To match our UI layout algorithm, we're going to change some of the functions in our hierarchy so that the return value from our apple function is passed into the pear function as an argument. Because we pushed all these stack frames at the same time on our first visit to our base lemon function, how are we supposed to pass the output of one function into the next? We've already pushed all the stack frames, which means we've already had to specify the arguments before any of the subtrees have actually run. If we're doing something like our folder search that doesn't rely on those previous results, this subtle difference in the order in which frames are pushed onto the stack makes no difference, because they're still processed in depth-first order. But if you need to feed the results of one recursive call into the arguments of the next one, you now have a problem. There are a couple of ways in which we can address this in our iterative implementation. The first approach is very similar to how we did our return value aggregation. On the way back up in post order, we reach into the parent reference and add the dimensions to the offset there. And now, because the offset value lives in the parent, we can read that modified value from the parent on the way down in depth first order rather than the potentially stale value stored in the stack frame as a function argument. To visualize this approach, instead of thinking about this as feeding the output of one function into the next, instead we store the value in the parent stack frame, and then when it comes time to execute the pear or grape functions, they can read and write the up-to-date value through the parent reference. And so even though this approach works, lifting up the function argument into the parent stack frame so that it can be referenced by siblings is more of a shortcut to provide equivalent functionality to our recursive function. And so for completeness sake and also just for fun, we're going to look at one final approach which is guaranteed to cover every possible recursive function because we're going to fully emulate how function calls work under the hood. And actually, there's only one thing left to emulate, which is return addresses. Remember how our iterative approaches used a visited boolean to track whether we're seeing this stack frame for the first time in depth first order or for the second time in post order after all the children have been processed? That means our iterative approach visits each stack frame a maximum of 2 times. In contrast, we also looked at the order of execution in a standard function call tree, and by tracking which line was executing, we saw that our parent functions are getting visited not just twice, but multiple times when we have multiple children. The reason for this difference becomes obvious when we look closer at the order in which we're pushing our stack frames. In our iterative approach, we push all the child stack frames at the same time in a loop. So if we're processing our stack from top to bottom, it's obvious that the parent stack frame will only be visited after all the children have been processed. Our recursive implementation, because it uses the standard function call stack, pushes the child stack frames one at a time and revisits the parent function again after every child returns. Each of these revisits allows us to do more processing after each subtree has finished. So what we want to do is modify our iterative approach, so instead of pushing all our child stack frames in a loop on the first visit, we want to push one stack frame at a time on each visit, emulating the concept of our normal function returns. Which also means that each time we revisit our parent stack frame, we're going to need some way to resume in the correct place. And finally, to bring our investigation full circle, you'll remember that the way built-in functions are able to resume the parent function in the correct place after the child function returns is because of the return address, an otherwise invisible piece of data that's stored in function stack frames. You might not have ever thought about this before, but imagine if the concept of returning to partway through a function didn't exist. Instead, whenever we returned from calling a child function, we just started back at the beginning of the parent function again. Of course, this would mean our one function would get run over and over again, and we'd get stuck in an infinite loop. Is there any way we could still get functions to work properly if this was the normal behavior? There actually is. What we need to do is manually keep track of where we were up to in the function, and a simple, straightforward way of doing that is by using a variable and a switch statement. Our state variable, which is an enum, defaults to 1, which means that when the main function is first called, we enter this first branch. We set the state to 2 before we jump to function 1. So now that when we jump back to the top of our main function, we can now progress straight to the next branch of the switch and correctly call function 2. In programming terminology, this is what we would refer to as a simple state machine, which really is just fancy terminology for something that has a finite number of possible states that it can be in, and behaves differently depending on the current state. So we're going to upgrade our iterative approach to use a state machine, essentially to emulate the concept of a return address. At the moment, we have this visited boolean to track whether we're traversing downwards on our depth first search or upwards in post order. We're going to take that visited boolean and convert it into a series of states that we can transition through each time we visit this function. The states that we're going to need to represent are exactly the phases we identified when we unrolled the loop in our recursive implementation. We have a state to represent our first visit, a variable number of states to represent each of our child functions returning, and a final state to represent that we're done. To make this a bit easier to work with, we'll simplify this down to only having 3 states: entry, children, and exit, and we'll use an additional child index variable to keep track of which child we're up to when we're in the children state. Let's walk through our implementation step by step. There's a bit of pseudocode going on here, missing break statements and that kind of thing, but you get the idea. When we first visit our root stack frame, we're in the entry state. So we do our various setup tasks like calculating the base size of the element, and then we progress the frame into the children state. Our next iteration, we're in our children state, so then we check if our child index is less than the length of our children, and if it is, we push a new child stack frame and increment the child index. This is essentially equivalent to executing a single iteration of a for loop at a time. We now continue our while loop around to the first child, which also progresses through its entry and children states, pushing the first of its children onto the stack. You can see how, in contrast to our previous iterative approach, which pushed all the children onto the stack at once and just visited them in depth first order, we're now also pushing the stack frames in depth first order, which means that when we return to the parent frame, we now have an opportunity to read the complete result of this previous child and pass it on to the next child's stack frame as an argument when we push it. Now, don't worry if you don't see the particular utility of an approach like this. I mainly illustrated these examples for completeness sake and also just to show you that with varying levels of complexity, it's possible to replace any code that uses recursive function calls with an equivalent that uses a stack and a loop. And while you'll likely never have to implement a full emulation of a call stack using a state machine, understanding how things work under the hood is really important. And I also just think it's really interesting. And now that you understand everything that's going on, here's a quick cheat sheet to help you convert your recursive functions into iterative equivalents. For all recursive functions, we need to create a stack. We can then push whatever the initial function arguments were for the recursive function onto the stack and create a while loop to process the stack one frame at a time. Next, we can lift any arguments that are just passed through from one recursive call to the next into the outer scope, including any context structures that were previously being used. Next, we need to actually process the top frame of the stack inside our while loop, and there's two ways to do so. If there's no additional code after the recursive call, that means we're only doing a depth-first traversal, and we only need to visit each node once, which means we can just pop each frame off the stack and process it immediately. If there is code after the recursive call, we need to execute that code in post order, which means changing our pop call to a peek. We also now need a visited boolean in our stack frame. Then when we visit our stack frame, if visited is false, we can set visited to true and execute our depth first code. But if visited is already true, we can pop our frame off the stack and execute our post order code. Now let's look at return values. If our recursive function is using a return value, but really we only need the final value that's returned from the topmost recursive call, we can easily implement this by just keeping a variable outside of the scope of the while loop and doing our aggregation there. Now, there are cases where we need to do processing on return values of subtrees rather than just aggregating to a single value at the top. And the way this often looks in a recursive function is that we're saving the return value of a recursive child call and using it for some other logic before returning in the parent. To access the return value of a subtree in our iterative approach, we need to include a reference to the parent stack frame in the child stack frame, so that the children can write their return values back to their parent. We can then also include a space for the return value in the stack frame, which means that when our functions are finished, we have a sub-return value that we can use for our update function, and then we can also reach through the parent reference to write our return value, which is equivalent to the native return statement. After return value aggregation comes the more complex case that the return values from one subtree need to be passed into sibling subtrees, like our UI position example. This is personally where I draw the "there's probably a better way to do this" line, for example using multiple passes over the data rather than trying to do it all in one big recursive function, but for completeness sake we'll take a look anyway. If it's just a simple pass-through from one recursive call into another and you don't have different handling of the results after each call, you can handle this by lifting the result out of the function arguments and instead storing it in the parent frame, reading it from there in depth first order, and writing it back there in post order in the same way we do it with return values. That way, when the next sibling is visited, it'll pick up the result from the previous sibling through the parent reference. And finally, if we have multiple child recursive calls and we need to do different processing at the parent level in between each of them, we need to convert our stack frames into a state machine and only push one child at a time on each visit before transitioning to the next state. All in all, I feel like recursive functions are a little bit more complex than people tend to give them credit for, but I think that's mostly because they have these hidden dependencies. That is, in order to really understand how recursive functions work, you need to understand how regular function calls work, how stacks work, and especially how tree data structures and tree traversals work. And I find that kind of frustrating because in my university at least, those concepts were actually taught in the opposite order, which is that recursive functions came first and tree data structures came later. And to make matters worse, I was taught recursion using examples like the Fibonacci series and factorials, which are even harder for beginners to understand because even though they represent a tree traversal like all recursive functions, rather than traversing a pre-existing structure like a file system, they're generating the tree structure on the fly, which makes it even more confusing to try and visualize if you don't really understand how recursion works underneath. And it seems like I'm not the only one. I ran a small poll and the results are overwhelmingly consistent with my experience, with most people learning about recursive functions before they learn about trees. This, of course, isn't a statistically significant sample size, but if you did a computer science degree or similar, I'd love to hear about what your experience was. And so there you have it. And just one final clarification. When NASA says that they don't allow recursion, what they actually mean is they don't allow recursive functions, that is, functions that call themselves. They still allow recursive structures. And I guarantee you there are plenty of graphs, trees, and linked lists being used in the code that's written at NASA. In fact, if you scroll down just a little further in the NASA safety guidelines, you'll see a reference to traversing a linked list, which makes it more or less certain. I hope you enjoy your newfound knowledge about the inner workings of functions.